Not every great scientific story has a happy ending. This is one of those. It's about two of the most brilliant minds of all time, Einstein and Werner Heisenberg, who found themselves chasing the same beautiful ghost, a single elegant formula for the entire universe. They were titans of physics on opposite sides of a reality-shattering debate. One was the old guard, the man who gave us our modern picture of gravity. The other was the young rebel, a founder of the bizarre, probabilistic world of quantum mechanics. And yet, for all their disagreements on how the universe worked, both men spent the last chapters of their lives consumed by the same dream. They were hunting for a unified field theory, a master equation to unite the two great forces known at the time: gravity, the silent architect of the cosmos, and electromagnetism, the force of light. This wasn't just a math problem, it was a philosophical quest. Was the universe a predictable, deterministic machine as Einstein desperately wanted to believe? Or was it all just a game of cosmic chance as Heisenberg's own work suggested? They were both chasing a theory of everything, but from completely opposite directions. This is the story of how they both got lost. Section 1. The world before the quest. To understand this obsession, you have to picture the physics world at the dawn of the 20th century. There was this incredible confidence in the air, a sense that the universe was finally being understood. The blueprint was already there. Back in 1860s, the Scottish physicist James Clerk Maxwell had done something amazing. He took two things that seemed totally separate, electricity and magnetism, and showed they were just two sides of the same coin, electromagnetism. With four elegant equations, he unified them, revealing that light itself was an electromagnetic wave. It was the first great unification, proof that the universe's messiness could be boiled down to beautiful, simple math. This success story was the holy grail for a young Albert Einstein. By 1915, Einstein had pulled off his own monumental feat. He'd completely reinvented gravity. In his theory of general relativity, gravity wasn't some mysterious force pulling things around. It was the fabric of space and time itself, bent and warped by mass and energy. Planets orbit the sun not because they're being pulled, but because they're following the straightest possible path through a cosmic dimple the sun has created in space-time. It was a stunningly elegant and deterministic theory. If you gave Einstein the state of the universe right now, his equations could, in theory, tell you what it would look like at any point in the future. It was a clockwork universe, but with a far more profound mechanism than even Newton had imagined. With these two pillars of physics, Maxwell's electromagnetism and Einstein's general relativity, the next step seemed obvious. At the time, they were the only two fundamental forces known to exist. Surely the force that governs galaxies and the force that governs light must be connected. Einstein even coined the term unified field theory for this grand project. After unifying space and time, matter and energy, he saw this as his final task, to bring gravity and light into one geometric picture. He dreamed of a final theory where the entire universe was nothing more than the geometry of space-time. But there was a problem. General relativity was a theory about geometry itself. Electromagnetism was a theory about fields that exist within that geometry. It was like trying to merge a house's blueprint with the laws of electricity flowing through its walls. They spoke different languages. Finding a common tongue would become the defining struggle of Einstein's life. But he couldn't have known his biggest obstacle wasn't the math. It was a revolution brewing that would shatter his classical dream for good. Section 2. The Quantum Schism. Just as Einstein was starting his solitary search, a new generation of physicists was tearing down the very foundations of classical reality. The 1920s gave birth to quantum mechanics, a theory so strange that it made curved space-time look like simple arithmetic. And at the heart of this revolution was a brilliant, almost shockingly young German physicist, Werner Heisenberg. In 1925, Heisenberg, in his 20s, laid the groundwork for a radical new description of the atomic world. Then, in 1927, he delivered the philosophical death blow to the classical universe with his uncertainty principle. It was an incredibly audacious claim. There's a fundamental limit, he declared, to what we can ever know about the universe. You can know a particle's position, but you'll be fuzzy on its momentum. Or you can know its momentum, but its position becomes a smeared-out probability. You can never know both perfectly. This wasn't a problem with our tools. Heisenberg argued it was a built-in feature of reality. Particles don't have a definite position and momentum until we measure them. Before that, they exist in a ghostly cloud of possibilities. The act of looking forces the universe to make a choice. To Einstein, this was just wrong. It was an abdication of what science was supposed to do. A man who built his career on an objective, predictable reality was now being told the universe was a game of chance. His reaction was visceral, summed up in his famous declaration, "God does not play dice." He couldn't accept a reality that was inherently random. He believed quantum mechanics had to be incomplete. There must be some deeper, hidden variables that, if we only knew them, would restore the perfect clockwork-like causality he believed in. This philosophical clash came to a head in 1935 with the EPR paradox. With his colleagues Boris Podolsky and Nathan Rosen, Einstein created a thought experiment to expose just how absurd quantum mechanics seemed. Imagine two particles created together, entangled so their properties are linked no matter how far apart they fly. If one has an upspin, the other must have a downspin. According to quantum mechanics, neither has a definite spin until you measure it. But the moment you measure the first particle and see it's up, you instantly know the other one, now on the other side of the galaxy, must be down. Einstein called this spooky action at a distance. It seemed to violate his own theory of special relativity, which said nothing can travel faster than light. How could measuring one particle instantly affect another? For Einstein, the only logical answer was that the particles did have definite properties all along. The information about their spin was a hidden variable they carried with them. Quantum mechanics, by not including this, was simply incomplete. The battle lines were drawn. On one side was Einstein, the aging revolutionary turned conservative, defending a knowable, deterministic universe. On the other were Heisenberg and Niels Bohr, champions of a new, strange, and probabilistic quantum world. This conflict fueled Einstein's quest for unification. He wasn't just trying to unite two forces, he was trying to find a theory so powerful it would derive quantum mechanics from first principles. Decades later, Heisenberg, a father of this quantum strangeness, would find himself on a similar quest, but for very different reasons. For Albert Einstein, the hunt for a unified field theory wasn't a side project. It was a 30-year obsession that defined the second half of his career, from the 1920s until his death in 1955. While the rest of the physics world was excitedly exploring the new quantum frontier, a frontier he'd helped open but now rejected, Einstein became an increasingly isolated figure, a king in self-imposed exile, searching for his holy grail. His strategy was to repeat the success of general relativity. If gravity was just the curvature of four-dimensional spacetime, maybe electromagnetism was some other hidden geometric property of that same spacetime. He was convinced that the physical world was just magnificent, intricate origami of the cosmic fabric. His first attempts were promising. One of the most alluring ideas came not from him, but from a little-known mathematician named Theodore Kaluza in 1919. Kaluza made a simple, wild suggestion. What if the universe has 5 dimensions, not 4? When he wrote out the equations for general relativity in 5 dimensions, something astonishing happened. The math naturally split into 2 parts. One was Einstein's original theory of gravity. The other, almost magically, was Maxwell's equations for electromagnetism. It seemed too good to be true. Gravity and light both tumbling out of a single 5-dimensional framework. A few years later, Klein refined the idea, suggesting we don't see this 5th dimension because it's curled up into a tiny circle at every point in space. Think of a garden hose. From far away, it looks like a 1D line. Get closer, and you see it has a second, circular dimension. In Kaluza-Klein theory, moving in our big dimensions is gravity. Moving around that tiny hidden circle shows up as electromagnetism. Einstein worked on the theory for years, but ultimately it didn't hold up. It was a beautiful idea that couldn't quite describe the real world. It struggled to predict the correct properties of particles like the electron, and it couldn't seem to make room for the new rules of quantum mechanics. Undeterred, Einstein kept going, exploring a whole menu of other geometric ideas. He played with concepts like teleparallelism, where spacetime wasn't just curved, but also had a kind of twist. But the effort he dedicated his final decades to was the theory of the non-symmetric field. The basic idea is this. In general relativity, the math that defines geometry is symmetric. The distance from A to B is the same as from B to A. Einstein's great hope was that if he dropped that symmetry, the new mathematical pieces that appeared would turn out to be the electromagnetic field. The symmetric part would be gravity, and the new anti-symmetric part would be light. For years, he worked on the equations. He published several versions, each one a monument of mathematical elegance. But he had an even deeper goal. Einstein hoped this ultimate classical theory would finally explain particles themselves. In his mind, an electron wasn't a fuzzy quantum probability. It was a tiny, stable knot in the fabric of his unified field. He believed particles would emerge from his equations the way a whirlpool emerges as a stable feature of flowing water. This would be the ultimate triumph, deriving the lumpy, quantum nature of particles from a smooth, classical field. But that triumph never arrived. By almost every measure, Einstein's lonely crusade was a magnificent failure. First, the math just led to dead ends. The equations were so fiendishly complex that no one, not even Einstein, could find a solution that looked anything like our universe. Second, the theories made no testable predictions. They were physically unproductive. They couldn't be used to predict new phenomena, and they struggled to even reproduce the known physics of the electron. And finally, most tragically, Einstein was trying to unify an incomplete picture of the world. While he was isolated in his office, lost in a maze of tensors, physicists were smashing atoms and discovering a whole subatomic zoo. They found new particles and, crucially, two new fundamental forces, the strong and weak nuclear forces. Einstein was trying to solve a puzzle while completely unaware that half the pieces were missing. He became a poignant figure, revered for his past but largely ignored by the present. The mainstream of physics had moved on. Einstein, the man who remade our cosmos, had become a relic, stubbornly chasing a classical vision of a universe that, as far as anyone could tell, just didn't exist. Section 4. Heisenberg's World Formula. Decades after Einstein started his lonely quest, a surprising new player entered the race: Werner Heisenberg himself. By the 1950s, Heisenberg was an elder statesman of physics. He was a father of quantum mechanics, the very theory that had so alienated Einstein. And yet, he too had grown dissatisfied. His issue wasn't with the probabilistic nature of the quantum world, it was with the growing chaos of particle physics. The new particle accelerators were discovering a bewildering array of subatomic particles: pions, kaons, lambdas. To Heisenberg, this felt messy. Surely nature couldn't be this complicated at its most fundamental level. So he set out to find what the German press dramatically called the world formula. It was his own unified theory, but it came from a completely different place than Einstein's. Einstein wasn't trying to get rid of quantum mechanics, he was trying to find its ultimate expression. He believed in a kind of radical simplicity. Deep down, there had to be just one fundamental thing from which everything else was built. His idea was a nonlinear spinor theory. Instead of starting with the geometry of space-time like Einstein, Heisenberg started with the quantum world. He proposed that the entire universe, all matter, all forces, could be derived from a single fundamental quantum field. From the churning of this one primordial quantum ocean, every particle and force would emerge like waves on the surface. He believed the mathematical rules of quantum theory and relativity were so strict that if you added just a few basic assumptions, the final equation would be almost inevitable. He thought he was on the verge of finding the single equation God wrote when creating the universe. But the climax came in 1958. At a major conference, Heisenberg took the stage to present his world formula. The hype was immense. Newspapers ran phonetic spellings of his equation. He himself, normally a cautious man, got caught up in the excitement, suggesting only a few technical details remained. But the reaction from his peers was brutal. His sharpest critic was his old friend, Wolfgang Pauli, known as the conscience of physics for his mercilessly high standards. Pauli had initially collaborated with Heisenberg, but grew deeply skeptical. When he heard Heisenberg presenting the theory as nearly finished, Pauli was furious. In a now famous letter, he drew an empty rectangle and wrote, "This is to show the world that I can paint like Titian. only technical details are missing. It was a devastatingly witty takedown. He was calling the theory an empty frame. To another colleague, Pauli reputedly dismissed the theory even more harshly, saying, "It's not even wrong." The ultimate scientific insult for a theory so half-baked it can't even be proven incorrect. Why did the world formula fail so spectacularly? The reasons mirrored Einstein's, but with a quantum twist. First, like Einstein's theory, it was mathematically shaky. Pauli's core objection was that the theory relied on mathematical tricks involving ghosts, states with negative probability, which he was sure would lead to paradoxes. Second, and most critically, it just didn't work. When other physicists tried to get real predictions from the equation, it failed to reproduce the known properties of the particles it was supposed to explain. It was a theory of everything that couldn't even get the existing things right. Heisenberg had taken a more modern path than Einstein, fully embracing the quantum world, but he'd made a conceptual leap that was just too ambitious, too soon. Like Einstein, he continued to work on the theory with a small group of followers, but for the wider physics community, the world formula was a dead end. Section 5. The Dream That Wouldn't Die. So why did two of the 20th century's sharpest minds tackling the same problem from opposite ends both fail so completely? The biggest reason is that they were trying to write a book before they knew the whole alphabet. They were trying to unify gravity and electromagnetism, unaware that two other fundamental forces, the strong and weak nuclear forces, were just as important. Their quest was like trying to solve a jigsaw puzzle with half the pieces missing. For Einstein, the failure was also philosophical. His 30-year quest was driven by his refusal to accept the quantum world. He was a classical thinker to his core, trying to build a 19th-century clockwork model for a 20th-century quantum universe. He was a general fighting the last war, unable to see that the rules of battle had completely changed. Heisenberg's failure was one of premature ambition. His quantum approach was more modern, but he tried to make one giant speculative leap to the final answer, believing pure logic would be enough. But physics isn't just math, it's an experimental science. The path forward wasn't going to be a single brilliant idea from pure thought. It would be a messy process of theory guided by experiment, and experiment correcting theory. And that's exactly what happened. The first truly successful unification after Maxwell's came in the 1960s. Physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak nuclear force are really two sides of the same coin, the electroweak force. Their theory made testable predictions, like the existence of new particles that were later discovered at CERN, proving them right. They won the Nobel Prize in 1979. The success of the electroweak theory was a profound lesson. It proved unification wasn't a fool's errand, but it also proved that the path forward had to be a quantum one. So, was the epic quest of Einstein and Heisenberg a waste of time? Absolutely not. Failure is the essential, if unglamorous, engine of science. Einstein established the grand ambition of unification that still drives physics today. Modern ideas like string theory are the direct intellectual descendants of his lonely crusade. His story is both an inspiration and a cautionary tale about the danger of letting philosophy blind you to physical reality. Heisenberg's dream of finding a single fundamental seed for all of reality also continues to echo in modern physics. The history of science is filled with these beautiful failures. They're the hidden scaffolding that supports our modern understanding, and they're often more instructive than the straightforward successes. And if you enjoy exploring these deep questions and grand narratives of science, consider subscribing. It helps us continue to tell these essential stories. In the end, we're left with the image of two giants walking different paths toward the same beautiful mirage. Albert Einstein, the classical purist, searched for God's blueprint in the smooth geometry of space-time. He wanted a final deterministic equation for an orderly universe, but found only shifting sands. Heisenberg's dream of finding a single fundamental seed for all of reality also continues to echo in modern physics. The quest continues today. Physicists are still trying to merge gravity with the quantum world, but they do so standing on the shoulders of these giants and on the lessons learned from their magnificent failures. The dream of a final theory is still alive, but it's now a humbler, wiser dream, one that acknowledges the immense and beautiful mystery both Einstein and Heisenberg so desperately sought to understand.
If you enjoy this kind of content, check out my other science videos and stay tuned for the coming ones.